Okay, well, I hope it's good enough for you guys, and we shall see. Okay, so today, this week is our last week of new content. We are going to cover chapter 12. I think it's chapter 12 of the book. Yeah, chapter 12. And this will be correlation, and linear regression. I'm looking at this, and I think normally the screen is like kind of doesn't go all the way to the top of the projector, and so it feels like we're at like the IMAX theater or something. You guys are in the front row. Okay, so we're covering correlation and linear regression. And again, this is our last week of new content. Hang on, let me just save this. So just to kind of recap where we've been in this quarter, up until the midterm, we kind of covered a lot of we started off with descriptive statistics, describing data, and then we moved a little bit into the realm of probability to get a foundation of sampling distributions, which led us to the central limit theorem. And that kind of formed the basis upon which we created confidence intervals, and that took us to the midterm. And then after the midterm, we then continued with hypothesis tests and of different kinds, t-tests and whatnot. And then we learned about chi-squared tests for categorical variables, and ANOVA, which is kind of allowing us to do like t-tests, where we're comparing numeric variables but across multiple groups. And so this week we are covering correlation and linear regression, and here we are exploring a relationship between two numeric variables. Okay, so a lot of the other ones we looked at two variables, but one was categorical. So for ANOVA and t-tests, we had a numeric response, but the quote-unquote predictor, or the thing that we were looking as kind of something to explain, was a categorical one. We would split them into two groups or three groups or something like that, hoping that that might explain some of our variation. Here we are looking at another numeric variable to explain the variation in our numeric response. Okay, so we explore the relationship between two numeric variables. Okay, so our response is numeric. To another So this is, in contrast to ANOVA, where we had a numeric response, but our but the variable that we used to explain the variation, or part of the variation, was categorical. So we can start off with just kind of a very, the most basic tool to explore the relationship between two numeric variables is the scatter plot, which is a graphic display. And all we do is we take our two variables, and we might call them x and y, and we just plot them against each other. Okay, so this is a very silly example, but it works well enough. Let's say we looked at a few dwellings, and we counted how many bedrooms there are and how many closets there are. Okay, and this and so we go to a place with one bedroom, and so let's say this is what it looks like. All right, so we go to a place with one bedroom and it has two closets. A place with two bedrooms, for whatever reason, has 6 closets. Okay, another place that has 3 bedrooms has 4 closets, and a place with 4 bedrooms has 8 closets in the house or whatever it is. Okay, and we want to know, is there a relationship between the number of bedrooms in a dwelling and the number of closets? Okay, the number of bedrooms and the number of closets. Okay, now from our personal experience, we would say yes, right? We would say houses that have lots of bedrooms will, in general, have more closets than houses or apartments with few bedrooms. Okay, so if you live in a studio, which I guess is 0 bedrooms, I don't know, or a one-bedroom apartment, you're not going to have 20 closets. Whereas if you lived in a mansion of many bedrooms, you probably will have many closets. Okay, and so we're just asking some silly question like this, and this is not going to be, I can't imagine a random sample ending up like this, but let's just say let's say this is a quote-unquote representative sample of the population. It's not, but for the sake of argument, let's say it is. We can create a plot. Okay, and all we do is we put the x on one axis and the y on the other, or we can just write bedrooms and 1, 2. Somehow I have to let's see. I don't know. Okay, something like that. And then I would just plot this. So if this is 2, 4, 6, 8, I would have to put a dot here and a dot somewhere around there. And a dot something like this. Okay? And so from these dots, it does seem that there's some kind of trend of going something like that, right? Some kind of overall trend of more bedrooms goes with more closets, right? Or vice versa, more closets seems to be associated with more bedrooms. Okay. And this scatter plot, it could be used to explore all sorts of things, but it serves as a basic tool, and it's actually very important that anytime you do regression analysis or correlation or explore this type of thing, the very first thing you should do is make a scatter plot, okay? Because we can calculate all of these statistics and things and do our analysis, but it doesn't give us the entire picture. And whereas the scatter plot, our eyes will be able to kind of discern things very, very quickly. Okay, so always make a scatter plot.
Eyeball it first, right?
Yeah, always make a scatter plot to eyeball it, exactly. Okay. Unless someone tells you for sure there's some kind of linear relationship here, okay? And so as we talk today, we're only going to focus on linear regression. Okay, sometimes this is called simple linear regression, or ordinary least squares regression. And the word linear here means straight line. Can a straight line explain the relationship between two variables? And regression is a very powerful tool in statistics. It is also perhaps one of the most misused or abused tool in statistics, just because maybe conceptually it's easy to understand, but there's a lot of kind of dangers, and I don't know if we're going to be able to cover everything in one week's lecture on the topic. Okay, so it would be as if I'm teaching you. I should say, okay, here to start the car, you put the keys in and you turn it like this. This pedal does gas, this pedal hits the brakes, and this is how you steer it. And I say, and that's pretty much all you need to know. Go ahead and drive. And so there's part of me that kind of cringes that this is all we're going to talk about regarding regression, just because I feel like I'm giving you just enough to be dangerous without the full kind of all the words of caution and things like that. And you know, our book only dedicates one chapter to it. You can take an entire course on regression, and if you see any statistical analysis in your future, I do recommend as kind of a next step class that a regression or an ANOVA class would probably be the next thing to take. But it's a basic tool, but very powerful, very useful. Also potentially dangerous in that you can, if you don't quite know what you're doing, you can start making all sorts of conclusions, thinking you do know what you're talking about when not really. So, okay. Anyway, linear regression. When we're talking about straight line regression, we just mean, maybe the dots kind of look like this. Our data point between x and y, they look like this or something. Maybe there's a little bit more spread in the clouds, but overall x and y, there seems to be some kind of straight line. So this would be linear. Whereas if you have anything where maybe the dots look like this, okay, of course with a little bit of so this would be nonlinear. Okay, and you can use regression, and something like this would be covered in a more advanced regression class. But in our class, we're only going to focus on linear regression. Okay, so a straight line can summarize the relationship. Maybe also another thing, maybe you get something that looks like this. Where you're kind of getting this cone. This would also be nonlinear. Okay, so our class, we're just doing this. Okay. Okay, and so when we talk about a relationship between, this is a y, by the way, this is not x and x, x and y. When we talk about the relationship between two variables, if after creating a scatter plot, it seems like a linear relationship is appropriate, we can kind of summarize that relationship with a value called correlation. Okay. Oops. Something. Okay.
Is that the same thing as correlation coefficient?
Yeah, correlation coefficient. Wait, correlation coefficient. And it's not spelled correctly. Coefficient. IENT, is that right? Yeah, okay, it just looks funny. All right. No, English, you and your funny rules. Okay, or exceptions, really. Okay, so the correlation coefficient, it's just like the mean or the standard deviation or anything like that. It's a statistic or a parameter if we're talking about the population. Okay, so a statistic, if based on a sample, or parameter if we're talking about the population. that summarizes the relationship between two numeric variables. Now, so the correlation coefficient is just calculated based on a formula, okay? Just like the mean is, right? The mean you calculate by adding up all the numbers and dividing by how many you have. And that formula applies whether it's a sample or a population. If you happen to be able to measure everything in the population, you can get the mean mu of the population. And if you only have a sample, you do the same thing and you get y bar or x bar of a sample. So the correlation coefficient, you just throw numbers into a formula and it spits something out. So it does exist even if the relationship is nonlinear, okay? However, the interpretations of it are only meaningful for a linear relationship. So I'll write that here, okay? So it exists even if the relationship is nonlinear, okay? But the interpretations are only meaningful for linear relationships. All right, let me pull up a picture from here. What's going on? Oh, this is weirding me out. Let's pop up. Okay. I got it. It's like 540. No, maybe even less. Oh, here we are. Okay. So let's zoom in here. Let me copy this. Is that looking okay on your screen? All right, good. Okay, so the correlation coefficient, we use the symbol R, okay? R is the symbol, and R can be any value between -1 and +1. Okay. You don't have to copy all of these pictures into your notes. I mean, you can if you want to, but you don't have to. This is on page 516 in your book. Huh? It's fun drawing this? Okay. And this describes if it's positive, so if R is greater than 1, the overall trend is what we call a positive direction, okay? So these are, direction is positive, right? And if R is negative, we say the direction is negative. Okay, so basically the sign of R is the sign of the relationship. Simple enough. Okay. And then if R is 0, then that means there's no relationship between x and y. Okay. R equal to 0 means no relationship between x and y. And if R is far from 0, meaning r is close to -1 or r is close to 1, then the relationship is strong. Okay, we have a strong relationship between x and y. Okay, so what exactly does all of this mean? I'll let you guys write that down, and we'll just write a few more things on the next slide. Okay. So I'm just going to kind of throw this in here again. Okay, so if r positive, what that means is that large values of x is associated with large values of y. Okay, and small x goes with small y. So that's what r positive means. Okay, and we can kind of see that. You can imagine if we were to draw, a pair of axes here, or a pair of axes here for x and y, and x and y. What we see is that, as x gets bigger, so as we increase this way, the y's also tend to get bigger. Okay, and of course, if we look at any individual point, that may not necessarily be the case, or any pair of individual points, that may not necessarily be the case, but overall there's a positive relationship. So things like people's height and their weight, overall there's a positive relationship. If you have large x, meaning you have tall, if you're tall, high height, generally you would weigh more than somebody who has a small x, meaning they are someone who is short, generally will weigh less. Okay, of course, on an individual basis, there's going to be differences that don't fit the trend, but overall, that's the overall trend. Large x goes with large y, small x goes with small y, and vice versa. R negative just has everything flipped around. R negative means large x goes with small y, and small x goes with large y. Okay, so we see that, over here. As x gets bigger, y tends to decrease. Okay, x, y, same type of thing here. So this could be, time spent practicing, and your performance if it's on a 0 to 100 scale or something like that. So more practice generally. Oh wait, that's backwards. Now that would be a positive relationship. More practice means higher score. Negative relationship could be something like temperature, outside temperature, and number of sweaters sold, or something like that. Okay, so if the outside temperature is high, maybe you're not going to sell a whole lot of sweaters. If the outside temperature is low, the store will probably sell more sweaters. Okay, something like that. That's kind of a silly example, but that's how we have positive and negative R. Regarding R strong versus weak, meaning R is close to 1 or -1, that means the variation in x explains a lot of the variation in y. Okay. Okay, so if you think back to ANOVA, we tried to break apart the variation, and we said, or we said the total variance is a combination of the variance between the groups and the variance within the groups. And we said basically the variance within the groups could not be explained by the existence of these different groups, and so that was what we called the residual. And with correlation, it's a kind of a similar concept, except now we don't have groups, we've just got different values of x. And we can say how much of the variance in y can be explained by the existence of different values of x. And maybe a lot of it can be explained. And in that case, we would have a strong correlation. Okay, so for example, so this is a very silly example, but let's say we measured everybody's height in inches and everybody's height in centimeters. Okay, but let's say we didn't fully know what this was, and we looked at all of the different values of heights in centimeters. Okay, and we say, okay, well, there's quite a bit of spread between, the shortest and the tallest, or the high values and things like that. If we knew the person's height in inches, we could perfectly predict what their height in centimeters would be. If the height in centimeters was the response and we knew the person's height in inches, we could pretty much perfectly predict their height in centimeters. So all of the variation in the centimeter values can be explained by the variation in the inch values. Okay, so that's kind of silly, but on the other hand, let's say we had people's height, and we also had, let's say we were looking at kids, ages 5 to 17, or something like that. Okay, so let's say we had the heights of a bunch of kids from ages 5 to 17, and we also had the kids' age. Okay, so we would see, a great range of heights, and if we knew the kid's age, that might explain a lot of the different heights. Okay, and we would see, the older kids are taller, and the the younger kids are shorter, and so a lot of the variation can be explained, but it doesn't explain it perfectly, right? Because if it explained it perfectly, that means all 5-year-olds would be the same height, all 6-year-olds would be the same height, all 7-year-olds would be the same height, and like magically on your birthday, when you go from 5 to 6, you would immediately jump from one value to the next or something. Now we know that's not the case, but knowing someone's age, and as far as kids go, gives us a very good idea of how tall this person is. Okay, and that's why when you go to the store, a lot of times for kids' clothing, they sell them by age. They don't sell it by, sometimes they sell it by your actual measurement. Like usually when you're an adult, you buy a shirt and it says, this whatever size it is. Okay, if you're a man, you buy based on your pants length, right? Because your age no longer explains the difference between heights. But when you're a kid, you can say, well, I need to buy age 8 clothes and age 6 clothes, or age whatever clothes, because that explains kind of what it is. So that would be a strong relationship. But yeah, once you're an adult, when you buy pants, you no longer tell the store, I'm 30 years old, so what size pants should I get? That would not help them, okay? Because at that point, the relationship between age and height is pretty much non-existent, okay?
What about like if you have somebody's height in centimeter in inches, and then you have their weight in grams and pounds. Is there any correlation?
Oh, okay, so you've listed off basically 4 variables. So it depends which ones you're pairing up, because here we're just looking at 2 variables at a time. So if you're looking at the 2 height variables, that would be a direct kind of pure relationship, and you're looking at the 2 weight variables, it would be a pure relationship. But if you're looking at any of the height and weight combinations, it's not going to be a pure relationship in that you can perfectly predict someone's weight if you knew their height. Okay, you know, if we're talking about pieces of cable or maybe pipe, let's say we're cutting different lengths of pipe, perhaps we can predict perfectly how much a piece of pipe would weigh if we knew how long was cut, how long of a piece was cut, because we're expecting, kind of this mechanical thing. But as far as people go, you can have 2 people with the same height that will have different weights. Okay. All right, so R weak basically means R is close to 0. Okay. Pretty much only a little bit of the variation in Y can be explained by X. Okay. And so that kind of explains the top row of pictures. In this bottom row, what we see is that this thing and this thing both have correlations of R equal to 1. Okay, so what you see here is that slope does not matter, does not affect R. Okay, so because this one is more steep and this is less steep, but the slope doesn't matter. The fact that there's hardly any scatter, or that pretty much all of the variation in Y can be explained by X, means that the R is 1.0. And also we have, less slope here than over here, but they're both kind of pointing in this downward direction, so that gives us an R of -1. Okay. Only when you enter something that's flat, where it's neither a positive nor a negative relationship, then you have R equal to 0. Okay. And here are just a whole bunch more pictures of R equal to 0. Okay. All right. Here's a little quiz. What if I have this? What would the R value here be?
That'd be like a strong one. It's still a relationship.
There's still a relationship. Okay, so R, remember, R only does straight line relationships, okay? Now, if we had to kind of summarize this overall with a straight line relationship, it would probably be something like this, if this was all the data I collected. Okay, and so in this case, we would have R is positive, and we'd have to look at the scatter. And so how much does knowing X tell us about Y? I don't know. But, it's not 100%. It's not 0. I would say, maybe plus 0.6, 0.7. I don't know, something. Okay, I'm just making up a number. I don't really know. But it's not 0, because overall, according to the data that we've collected so far, it seems like larger X goes with larger Y. Now, if I had collected even more data and it turns out that these data go down like this, and I included all of these data points, then R would be probably 0, right? Because in that case, I'd get something like this. Okay. So if I include these data points, I would probably get r equal to 0 here. Is this okay with you guys? Okay, so let's, and every time I teach this, there's always a little part of me that's hesitant, but I think there's still merit in learning how r is calculated. So we're going to calculate r by hand for a very small data set, okay? Now, but truth be told, in real life, you never would calculate r by hand, okay?
Is that what R
I think the program R is kind of a play on a few things. Probably R for correlation, but also it was based on a programming language called S, which was developed by a private company, probably named for statistics. But then they made an open source version of pretty much the same thing called R and whatever. But so I don't exactly know. But anyway, we're going to learn how to calculate R by hand, and I think there is some value in kind of the same way I had you guys. Well, I don't know. I had you guys learn how to calculate the standard deviation by hand, and I don't know if that enhanced your understanding of what the standard deviation is. Maybe, maybe not. Not really? Okay. Well, if you've forgotten, the standard deviation is a measure of the spread, right? And you calculate how far each point is from the mean, okay? And then we're kind of basically taking the average of that distance from the mean, except it's not the average. We square them and then we add them up and divide by n minus 1. But it's kind of the idea of how far is something from the mean.
68% and 95%.
Yeah, and it serves as a very useful thing with getting z-scores and things like that.
Isn't it kind of like a measure of precision?
Yeah, exactly. It's a measure of the spread in our data. Okay, so for the correlation, basically what we're doing is we're taking a sum product of z-scores. Okay, we're going to multiply z-scores together, and then we add them up, and then we kind of take the average of that. Okay, so R, the formula for it is n minus 1, but we're basically multiplying together the z-score for x and the z-score for y for all data points in our okay. And so I'm going to kind of maybe expand this a little bit. So if you think of the z-score for x, that is the difference between x and the mean of x divided by the standard deviation of x. So this is each x in our data times, and we're going to do the same thing for each y in our data, divided by the standard deviation of y. Okay. So for every data point, though, in our data set, the standard deviation of x and the standard deviation of y is going to be the same. Okay, because the standard deviation of x, this is standard deviation of x for all data points. Okay, so it's the same for everything. Same thing for y. Okay, pretty much the same thing except with y for all data points. So that means with the sum product, I can factor out s sub x and s sub y. So I'm going to be left with 1 over n minus 1 times 1 over s sub x times 1 over s sub y. And I'm going to have the product basically the distance each point is from their respective mean. Alright, so let's try this out with our very simple data set of bedrooms and closets. One, two, three, 4 bedrooms, 2, 6, 4, 8. And I want to draw this. I have already drawn this in my notes. Let me scroll back. Can I copy this? Okay, I'm going to calculate a few summary statistics over here. Okay, so X bar, I would add up these 4 data points and divide by 4, and I would get 2.5. And Y bar, I would add up these 4 data points and divide by 4, and I would get 5. And I'm going to plot those just to kind of give us a reference here. So here's X bar equal to 2.5. This blue line represents that. And right here is Y bar equal to 5. Okay. So we're going to look at each data point. And so let's take a look at this guy right here. Okay. So this guy is he is 3 units below Y bar and 1.5 units below X bar. Okay, so I'm going to make a table here. I'll say this is X, this is Y. 1, 2, 3, 4, 2, 6, 4, 8. And we're going to say how far below are you from X bar and how far below or above you Y bar are you. Okay, so this guy is 1.5 points below X bar and also 3 points below Y bar. Is that okay? Alright, and I'm going to do that for all of our data points here. So this, the one with 2 bedrooms is 0.5 point above X bar and 1 point below Y bar. Oh wait, no, I have that backwards. It's 0.5 point below X bar and 1 point above Y bar. This one is 0.5 point above X bar and 1 point below Y bar. And this one is 1.5 above and 3 above. And so this one will be the product of xi minus x bar times yi minus y bar. Okay, so I'm doing this. So if I multiply negative 1.5 times negative 3, I get positive 4.5. Over here I get negative 1/2. Here I get negative 1/2. And here I get positive 4.5. Okay, and so if I add all of these up, I get a total of 8. Okay. Let me just a quick. Okay. If I calculate the standard deviation of x, okay, basically I calculate the standard deviation of 1, 2, 3, 4. The standard deviation of x is going to be 1.291, and then the standard deviation of y is going to be the standard deviation of these 4 numbers. That would be 2.582 with a little bit of rounding. Okay. So plugging all of this in to our formula for r, I get r is equal to 1 over 4 minus 1, or 1 over 3, times 1 over 1.291 times 1 over 2.582 times, so this sum product, which is right here, is 8. And if I do that, I get r equal to 0.8. Is that okay? Okay, and so what we can see here is that pretty much these products add up to kind of create this thing. And it's a coincidence that, you know, when you multiply all of these things together, you get 1 over 10, which is kind of a nice number, but I picked these numbers as such to kind of give us this nice thing. But we can see how each data point contributes to the calculation of the correlation coefficient. Okay, we can see that this data point is below x bar and below y bar, and this data point is above x bar and above y bar. Okay, so they contribute in the positive direction, where low x is associated with low y and large X is associated with large Y. So that these 2 points contribute in the positive direction, right? Because if we think of where the middle is, being X bar and Y bar, we expect points that are below the middle in terms of X would also be below the middle in terms of Y, and this point is. And this point is above X, above the middle of X, and it's also above the middle of Y. So these 2 points contribute in the positive direction. We can see that. We have positive 4.5 and positive 4.5 for those 2 points. These 2 points, on the other hand, contribute in the negative direction, right? Large X goes with small y and small x goes with large y. What we're seeing here is that this data point is smaller than the middle of X, but it's above the middle of Y. So it's contributing in the negative direction. Okay. However, the magnitude of these contributions are much smaller than the magnitude of these contributions. And so we see their contribution to the total to be only negative 0.5 in the negative direction. And so when we add them all up, it adds up to 8, still in the positive direction. Okay. And so, you know, if I had rearranged the data points, you know, in some other fashion where, you know, I have points like this, okay, we would get a negative thing, not -1, but something in the negative direction, because these 2 points on the extreme contribute in the negative direction, and these ones contribute in the positive, but in a much smaller way. Okay. what if I moved these data points out to here and here, and I get rid of the ones in the middle? What would happen? Yeah, so if I have something looking like this, what would our correlation between x and y be? 0, right? Because the positive contribution and the negative contribution would cancel each other out. Okay? Okay, so yeah, again, maybe in your homework you have to calculate correlation coefficient by hand for a data set no more than 4 or 5 points. Okay, and you can kind of see how each data point contributes in the positive or negative direction. And again, but in real life, it is much faster and more accurate for a large data set to just throw it at the computer and say, calculate correlation for me. Okay. Are there any questions on this so far? Okay. Let's see. I'm thinking of just kind of powering through again and maybe finishing a little early, if that's okay. If you need to, huh? Good. That's okay. All right. So just like anything else, what we observe in a sample, we're hoping is representative of what happens, what's in the population. But the question remains, okay, maybe in my sample I observe correlation. Does this mean in the population correlation exists between the two variables? Okay, is there, just because we observe something in the sample, does that mean there is, that it actually exists in the population? So for example, we asked the same kind of thing when we did t-tests. We might have taken 2 independent samples, and the means of our 2 independent samples aren't exactly the same. Does that mean the respective populations have different means as well? And that really depended on basically the magnitude of the difference between the 2 samples, and how much variance there was, and the size of your samples. Okay, so we have to do a similar type of test for the correlation coefficient. Okay, so let's see. Let me write this. Okay, this is test for significance correlation. Okay, so we may observe correlation between x and y in a sample. Okay, so keep in mind each subject in your sample, or each individual in your sample, have both an x and a y measurement. Okay, these are not just values of x and unassociated values of y. Okay, we're not just taking two numbers and mashing them together. They're each value, or I mean not each value, each individual has 2 values associated with it, x and y, and we want to know, is there a relationship between x and y across all individuals? Okay, so So we observe correlation between x and y in a sample. Does this mean there's correlation between x and y in the population? Okay. So, if we think of our bedroom closet example, the correlation that we observed was 0.8, okay? And we're going to say this was a random sample, even though I have my doubts. But we're going to assume it's a random sample where n is equal to 4. And actually, I'm not sure if we could even do this with n equal to 4.
N needs to be bigger?
I feel like our n needs to be bigger, but I don't know the rule off the top of my head. But maybe n is 4. N equal to 4 is fine. Okay, so we want to know, does this mean there's correlation that's significant in the population? You know what? I think n equals 4 is fine, actually.
Isn't it? You log it?
We don't. We perform a hypothesis test, okay? And so our null hypothesis would be that there's no correlation. No correlation between x and y in the population. Okay? Or symbolically, we write that rho equals 0. This looks like a P, but it's the Greek letter rho, okay? This is Greek letter rho. Okay, which is the Greek's analog to R. Okay, so I don't know, statistics, you have sigma for standard deviation of the population and S for standard deviation of a sample, and here we have rho for the correlation in the population and R for the correlation in a sample. Okay, and then the alternative would then be that there is correlation, or you have positive correlation, or whatever you might want to say. Okay, so you can say rho is not equal to 0, or or whatever, rho is greater than 0, or rho is less than 0, whatever you want to say. Okay. It looks like a P, but okay. And without getting into how we arrived at this thing, the test statistic is calculated with this. It is a T. It follows a T distribution, actually. Okay. And I'm trying to recall my mathematical statistics, but I don't actually remember why. Okay, so anyway, you punch this in here, and then you would look it up in the T table. And here's the catch. The degrees of freedom is equal to n minus 2. Number of data points minus 2. And it's minus 2 because 2 dots form a line. So if you only had 2 dots, you'll have a correlation of 1, right? Because they always form a straight line. So it's only until you throw in a third data point when you can begin to ask, are these in a straight line or not? Is there predictive power here or not? Okay, so let's try this out. We have 4 data points. R is equal to 0.8. Let's just go with there is correlation between bedrooms and closets, and we will use the maybe we'll use a one-sided alternative. Okay, so no correlation versus positive correlation between bedrooms and closets. Okay, and so we punch in this thing, and we have 0.8 times the square root of 4 minus 2 over 1 minus 0.8 squared. What is this? 2 divided by... I get, my test statistic is 1.89. And I will look this up with degrees of freedom equal to 2. So I go to my t-table, 2 degrees of freedom. Oh, look at that. 1.88, actually, yeah, 1.886 if I have everything punched in here. And so this is one of the rare occasions where my critical value is actually equal to the value in my t-table. So it tells me that my upper tail probability is 0.10. If I keep all my decimals here. Okay, so that doesn't happen very often where the thing is the critical value, but so my tail is, it's not a range, it is 10% or very, very close to it. And because I have a one-sided test, this becomes my p-value. So my p-value is 10%. Okay, and so now the question is, well, does this convince me that there's positive correlation between the number of bedrooms and the number of closets?
Yes?
Well, I would say if we're using alpha equal to 5%, which is kind of our standard, our p-value is not smaller than 5%. So we would say, no, this does not convince me. Okay, and so what does this mean? Let's just talk a little bit more about our p-value equal to 10%. So we got p-value equal to 10%. All right, and so remember, our p-value is the probability of observing our data if the null hypothesis were true. Okay, so what was our data? Our data were 4 data points. We had 4 data points where the correlation was equal to 0.8. Okay, so p-value of 10% means, you know, this means if you took me with I don't know, like you gave me 4 darts and I just kind of threw them at a wall, right? And they just land somewhere on the wall. Okay, now the chance is that they might form a pattern. Okay, when I just throw 4 darts, you know, at the wall, they might form a little bit of a pattern. Okay, they might seem to form some kind of correlation. Okay, and so you know, if we threw, so this is kind of just the idea of picking 4 points completely at random. Okay, now if you were a professional dart thrower, then maybe this is not a good example, but this is just the idea that we're kind of just throwing, you know, some darts into the sky or whatever, and then they land on our target. Okay, so if we threw darts at a wall, okay, what is the probability that by random chance alone the 4 darts form a pattern that shows a positive linear correlation of at least 0.8.
Are you equating throwing darts to points on a scatter plot?
Like getting those observations.
Yeah, well, I'm equating throwing darts with randomly selecting 4 random points on a scatter plot, kind of. Yeah. That's
Make sure I understand it.
that's the idea I'm going at. In life we don't have very many purely random spatially generating
Right.
things. Like, I guess you can leave a sheet of paper out and see where 4 raindrops would hit, but usually it's like the raindrops are coming down too fast or something like that, you know? So, we don't have a whole lot of, but I don't know, 4 darts.
Okay.
If you kind of just close your eyes and go,
It
boom.
works. I was just making
Yeah.
sure that I understand it.
Yeah.
I wasn't criticizing.
Okay. Yeah, so if we picked 4 points at random on a scatter plot, what's the probability that they kind of form a pattern where we can just not artificially, but just measure a correlation of 0.8? That would happen about 10% of the time just from random chance alone, okay? So okay. Well, it's also not hard to imagine just because it's only 4 darts, right? If I had 100 darts and I got correlation of 0.8, then that would not seem to be a random occurrence, okay? Then you'd say, oh, well, something is going on, okay? But 4 darts, it's easy to imagine this kind of happening by random chance, okay? And so, one of the cautions of testing for significance is that if you take any large population, it will almost certainly be kind of significant, almost, just because in the formula we have n minus 2, and this kind of forms in the numerator, and so if you get any large enough population, this will just get big enough where it's quite significant, unless r is extremely close to 0. Okay, so anyway, this is not then convincing. Our data set of 4 points does not convince us that there is correlation between x and y in the population. Okay. Again, this does not mean that there is no correlation. We can never say we accept the null. It just means we don't have enough evidence to say that there is. Chances are, if you looked at 40 more houses or even 20 more houses, you would definitely see positive correlation between x and y. Okay. Is that okay? All of this correlation stuff? Just enough to be dangerous, right? Okay, I'm going to flip to the next slide. All right, so now we want to talk about linear regression. So in linear regression, what we are doing is we are creating a model to try to predict y based on x. Okay. Based on x. Okay. And so a model, think of this as like a model car or a model train. It's a representation of the real thing. Okay. It's not a perfect representation, but it's supposed to kind of give us an idea of how x and y are related. So, if we, whatever two variables might be, if we're looking at someone's height and someone's weight, perhaps there's a lot of things that go into explaining someone's weight. Okay, their height, their diet, how much, they exercise, their genetic background. There's all sorts of things that can go into explaining someone's weight. Maybe height is one of those things. Okay. And with linear regression, we're just using one numeric variable to kind of predict y. Okay, we're using one x to predict y. And so if we think of what a line looks like, okay, so from algebra, you learned y equals mx plus b, okay, or in other words, you have y is equal to slope times x plus intercept. So in statistics, we will use the same idea, and we're going to say each data point y sub I is equal, and we just kind of rearrange our terms. We're going to say is equal to an intercept plus slope times x, okay, the equation of a line, plus, so this is the model, e sub I being our residual, okay. So this over here is the linear model, and this is our residual, or in other words, just individual differences. So perhaps x can explain why certain things are larger and certain things are smaller, but it doesn't explain everything, and so the part that remains unexplained is called our residual. Okay, and symbolically, I just want to make sure I'm using the same symbols as our book, just because every textbook uses different letters. Okay, so we have beta 0 plus beta 1x plus epsilon I. Okay, so this is the relationship that exists in the population. Okay. We wish we could figure this out, but we won't know what this is. Okay. We don't know this is the true relationship. Okay. Our estimate of this relationship is y hat. Our prediction for y is equal to b0 plus b1x. Okay. So I have a b0. So b0 would be, I'm sorry. So let me kind of just show you. So the intercept would be b0 and the slope is b1. Okay. So it's intercept plus slope times x, or intercept being b0 or beta 0 here and beta 1 times x. And then but this is the true relationship. Our estimate of this is just this, okay? And because we can't estimate the individual differences, because that's just left as kind of, this is unexplainable and we have no prediction, it's not going to be part of our estimation. Okay, so this would be our estimated intercept. And our estimated slope.
Is the beta, is that for the population and the small b for the individual numeric value?
I'm sorry, your question again?
The beta symbol.
Okay, yes, okay. So what we're saying is that in the population there is some relationship that actually exists between x and y. Okay? What we're saying is that overall, if we can look at all humans or something, there is some relationship that defines that someone's weight based on their height. And that relationship is this with the betas, okay? But because we can't look at the population, we have to estimate it using the data that we have, okay?
Right.
And so our best prediction is the thing with the hat and the bees.
Right.
And we distinguish it from what's in the population by using B instead of beta.
Right.
Okay, so this is our prediction, or our estimate of the true relationship. Okay. All right, and so when we pick out a line as an estimate, how do we choose which line is the best? Okay, and so so I'm going to use this thing still, but let me just blow it up. I should have get rid of these. All right, we'll just pretend these little extra lines don't exist. All right, so I'm trying to create a line to summarize the relationship between bedrooms and closets. Still. And so we have, what line is the best? And I'm going to draw a couple lines here, okay? So one line will look like, and it's very hard drawing a straight line on my computer. But that's one, okay? And then here I'm going to draw another proposal line. And that is, hang on a second, I have to do some math here. Okay. And the other one looks like why is it so hard to draw a straight line? Okay. So here's another line. All right. Which line does a better job of fitting our data? Okay. Or, which line, quote, fits the data the best? Okay. And so we are going to I'll write the equations of each line here. So the green line is y hat equal to 0 plus 2x. Okay, and the blue line is y hat equal to 1 plus 1.6x. Okay, these are our two lines, and we're asking which line does a better job of fitting, okay? And so these are actually both pretty good lines. You know, it's certainly better than I'm going to just, you know, somebody said, the best fit line is this, y equal, you know, this one is just y hat equal to 5. You don't have to draw this one, okay? Y hat equal to 5 just meaning I don't even need to know how many bedrooms are in the house. I'm just going to predict it has 5 closets, right? This is just saying, yeah, I've looked at all the you know, the average house in America has 5 closets. That's good enough for me, okay? Don't tell me how many bedrooms. You want to know how many closets I predict? I predict 5, okay? And that won't be terrible. It's not going to be a terrible thing. You're probably going to be closer than whatnot, but we can do better by saying, well, you know what? If we take into account how many bedrooms the place has, we can get a good idea of how many closets the place has. Okay. And so what we have to do is we're going to introduce an idea of what we call a penalty. A penalty is we make a prediction, and if it's off from the actual value, we incur a penalty. Okay, and the idea is we want the line that creates the smallest amount of penalty, meaning its predictions are as close to reality as possible, or it's closer to reality than any other possible line. Okay, so this is if our prediction is, you know, off, then we incur a penalty. Okay, sometimes it's called the loss function, whatever, you know. And so we want the line that minimizes our penalty. Okay. And so when we talk about ordinary least squares regression, okay, OLS, ordinary least squares regression, it gets its name because the penalty is known as the square of the residual, and it is the one that gives us the least amount of squared residuals. Okay, OLS, which is what we're doing, this will give us the smallest penalty when we use the squared residuals method. Okay. All right. So what is a residual? It is the difference, and I'm going to use a pencil line. It is the difference between the actual data point. So in this case, I have a data point right here. Okay. And if x equals 3, according to this line, I am predicting it would be equal to here. Okay, so for blue, so for the blue line, when x equals 3, we predict y hat is equal to 1 plus 1.6 times 3. Okay, And so our prediction for y hat is 5.8. We are predicting 5.8 bedrooms, or I'm sorry, 5.8 closets. Okay, and in actuality, our data point says there were only 4 closets. Okay, so our residual is the difference between the actual and the prediction. So I do 4 minus 5.8. I have a residual of 1.8, and the squared residual would be 1.8 squared, which is, I don't know what that is, 3.24. Okay. For the green line, when x is 3, our prediction y hat would be 0 plus 2 times 3. We're predicting 6 bedrooms. Okay, actual 4, so our residual is equal to 4 minus 6, negative 2, and our squared residual would be negative 2 squared. We get a residual of 4. Okay, so for the green line, we're predicting right there. We're getting a difference of that. Okay, so if I draw, so essentially we're taking the residual and we're squaring it. So the area of this box is 4, and the area of this box is 3.24 or something like that. Okay, and we're doing this for all 4 data points. Okay, is this okay? All right, and so let me crap. Let me just finish making a chart here. Again, calculating residuals by hand. So let's say, okay, so this will be x is 1, 2, 3, 4, and y hat for blue, and this will be residual for the blue line, which I've already erased, and we'll do residual squared over here, and then I'll do it for y hat for the green, the residual for the green, and r squared. Okay. So blue again was y hat is 1 plus 1.6x. So what do I have? I have 2.6 sorry, 4.2, 5.8, and 7.4. Oh, and the actual y's are 2. So I'm sorry, I put r's here. This is embarrassing. These are supposed to be e's, and not residuals. They're e's. I apologize. Little e here. Okay, not epsilon. Okay, so e is 0.6, and what was it? 1.8, 1.8, and 0.6. So I have 0.36, 3.24, 3.24, and 0.36. supposed to be the and then over here I have my predictions are 2, 4, 6, and 8. So I have no difference between the actual and but over here I have a difference of 2. I should list off the actual y's. Our data are x, y. Okay. Okay, and so the sum of our residuals over here, sum of the squared residuals over here is 7 point, no, shoot, what is it? 3.24 plus 0.36 times 2. Yeah, 7.2. And over here, the sum of the residuals squared is 8. And again, we are looking at the difference between the actual data and our prediction for it. So the green line predicts the number of closets for the place with 1 bedroom and 4 bedrooms perfectly. There's no residual there. Okay. However, for the place with 2 bedrooms and 3 bedrooms, there is a residual, and we square that and we get 4. Okay. The blue line doesn't predict any of these places perfectly, but so we get residual for all of them. But when we square them and add them up, we get a total sum of squared residuals of 7.2. So according to ordinary least squares regression, the blue line is the better fit. Okay, so using the OLS criteria, blue line is the better fitting line.
So you've just taught us how to decide between two lines, but you haven't taught us how to make the best line.
Correct. But this is to illustrate how OLS picks out the best line here. Okay. Now there is, I also have to note, well, not have to, but there is another criteria that uses not the squared, and it just uses the absolute values of the residual. And in that case, we would see here this one adds up to 4, and this one adds up to like 4.8 or something like that. And in that case, the green line is the better fit, okay? Or it actually is the best fitting, and it's called median regression or quantile regression or something else, okay? It's less commonly used, but it does exist, okay? But that uses a different penalty, and I would say ordinary least squares is kind of the accepted standard of what's expected in terms of picking out the best fitting line, okay? So anyway, yes, that brings up a very good question. Well, how am I supposed to pick out, I can't just keep drawing lines and have come up with different slopes and different intercepts and try to figure this out. Well, luckily for us, some very smart people, all right, and if we did calculus, we could derive how to get this, but basically some very smart people came up with this formula for picking out the slope and picking out the intercept that will give us the least squares regression line, okay? And so I'll give you that here, and we won't even have to worry about deriving it, and just know that this formula will give us the best fitting line, okay? And also, in fact, when you do regression on the computer, you just say, computer, give me the best fitting line, and it spits it out for you. It uses the formula, but that will be the line that fits the best. Okay, so the OLS line, okay, will have slope B0 equal to R times standard deviation of X divided by the standard deviation of Y. Okay, and it will have intercept. Oh, I'm sorry, did I say B0? Oh, I'm such a mess. This is B1. There's so many things. And intercept B0 equal to Y bar minus B1 times X bar. Okay, so you just need 5 numbers. Okay, so to calculate OLS line, or the linear regression line, whatever you want to call it, you need 5 values. X bar, Y bar, the standard deviation of X, the standard deviation of Y, and the correlation between X and Y. And if you have those, you plug them in here. You have to calculate B1 first, and then you can calculate B0, and then you will throw them together and you get Y hat equals B0 plus B1X. This will be your ordinary least squares line. Okay. And this minimizes the sum of the squared residuals. That's why we call it least squares regression. Okay, there is a nice little thing in that if you take the correlation, okay, and then you square it, for ordinary least squares regression, this gives us this quantity called R squared. This is known as the coefficient of determination. Okay, and this, again, this relationship works only for linear regression. In more complicated regression, there's another way to calculate big R squared. Okay, but it's convenient to that R squared is R squared. This is the coefficient of determination, and this is the percentage of the variation that can be explained by the model. So, if R is equal to 0.8, then R squared equals 0.64. Okay, and so just kind of like in ANOVA, we broke out the variation into part explained by the model and the leftover variation, the residual. In the same way, we can kind of do the same thing, and we can say 64% of the variation in closets can be explained by the number of bedrooms, and then the other 36% is just individual differences from house to house. Some houses just have more closets, or some houses have fewer closets, and that part can't be explained. Okay, but if we looked at houses and the number of bedrooms, we can explain about 64% of it by knowing the number of bedrooms. That's the coefficient of determination.
64%
the variation in y.
In y, so the 64% of quadrants.
Yeah. Whatever y is.
Right.
Yeah.
I'm just connecting it.
Yeah. Okay. So I would feel irresponsible if I just left it here. So I have to give you some warnings about what not to do with regression, just because I started off saying this is perhaps one of the most abused tools. So I have to at least say drive safely, wear your seatbelt. So let's talk about this. It'll be quite exciting when we have self-driving cars, right? And then we don't have to worry about. Well, we're hoping they're going to be much safer than human drivers. Okay, so warnings. Okay, don't use regression to make predictions outside of the range where you have collected data. Okay, so here's a common thing that people do is you have data that looks like this, okay, and then you fit a regression line and it goes like this, okay, and they say, oh, well, that's great, I look at my r-squared and I get like 0.9 whatever and things like that, and I say, oh, okay, well, that means in when x is out here, it's going to be there. This is their prediction, okay? This is terrible, okay? Because we don't know, because we've only collected data from here to here, right? So this is the range where we have collected data. Okay, we only have data here. Okay, and so we have no idea if the true relationship goes like this or if it goes like this. We don't know. Right here, it looks like a linear relationship, but out here we don't know. Silly example, let's say you had a child and you were measuring the height of your child from age 3 to age 13. And every single year, your child gets taller. And you're like, for the last 10 years, I've been measuring, every 2 months, I've got, and my child has grown this. I have 60 measurements, and I see this very strong linear relationship between time and height. And based on my thing, when I predict that when my child is 80 years old, he's going to be 27 feet tall, okay? Or something like that, right? That we know that's ridiculous because we know people, kids grow until they get to, adolescence or adulthood, and then they stop growing, okay? But people do nonsense like this all the time. You just change. If we replace, age and height with, current year and something about the economy, suddenly people are like, oh, in the year 2050, we're all doomed, or this is going to happen. We don't know what happens in the future, okay? So we don't know. So don't try to predict the future is what I'm trying to say, okay? Well, then what's the point, right? But it's very good for trying to just extrapolate, something in between the range where you do have something, okay? Watch out also for outliers or leverage points, okay, or places where you have very few measurements. Yeah, so a leverage point is a data point that is far away when it comes to the x value, it's far away from the other data points you have collected. Okay, so
What's different from an outlier then?
so I'll explain. Okay. Okay, so let's say you wanted to know, is there a relationship between IQ and shoe size? Okay, what would we expect to see? We would expect no relationship, right? We would expect people with big shoes, and well, some of them will have high IQ, some will have low IQs, something like this, right? So if we created a regression line, we would expect to see something like this, right? No relationship between shoe size and IQ. Okay. If okay, let's say we got Shaquille O'Neal. All right. I don't. We'll give Shaquille O'Neal. So we'll say Shaquille O'Neal has very, very big feet. Okay. And I don't know his IQ, but let's say he has a high IQ here. Okay. He acts as a leverage point, and then suddenly, because he's the only one out here, the model will try to fit him. Okay. And so we would incur you'd end up getting a model that looks kind of like this. And so now suddenly, because Shaquille O'Neal has giant feet and maybe has a high IQ, we're now seeing a relationship between shoe size and intelligence, a positive relationship. Okay, and so this guy, because regarding x, this is out here, this is considered a leverage point. So this data point is far from the others regarding with respect to x. Okay. An outlier is anything that is a data point that kind of doesn't fit the overall trend line. So an outlier could be someone way out here or whatnot. Okay, you don't have to worry so much about outliers if they're in the range of everyone else with the x, but you do have to worry about them if they're far away from everybody with x, because they exhibit or will exert what's considered leverage, high leverage. Okay. Now, it's not necessarily bad to have leverage points, okay, or values out here. But what you want is you want multiple measurements out here, okay? If you're going to include somebody with abnormally large feet or high shoe size, you want to include other people with unusually large feet. Otherwise, that one individual will exert a lot of influence in the model. So you want to make sure you have multiple measurements out there. Okay. There's a lot of other warnings I can give you. Maybe another one is just kind of the correlation is not causation, right? This is the other. So just because two things seem to happen together does not necessarily mean one causes the other. Okay. They might very well be, but there could also be something else explaining what's going on. So I feel like at least this gives you some sense of caution. But there you have that. Okay. Okay. We'll end there, and we'll see you guys next week. It'll just be a review. So if you have any questions about anything, bring them, and I'll do my best to address them.